So I also want to talk about a few facts about the modulus of a complex number. And so I want to point out that as we saw previously, the modulus of z and the modulus of z conjugate are the same, just geometrically. That makes sense. Algebraically, it's easy to check. The real part of z, and the same is true actually of the imaginary part, are always between the modulus of z and minus the modulus of z. Likewise with the imaginary part. It turns out that if we were to take the modulus of a product, so z times z prime, that's the product of the moduli. Likewise with a quotient, so z over z bar, z over z prime, if we take the modulus of that, that'll be the modulus of z over the modulus of z prime. I would encourage you to actually get out paper, write z equals x plus iy, and check all of these things for yourself. Okay, so these are important facts that we'll use over and over. So that's a few facts there. One more, just while we're on the topic. It turns out that a complex number is 0 if and only if the modulus of that complex number is the number 0. Okay, and so that's one thing to check, is that every complex number besides 0 itself, but every complex number has a non-zero modulus. Okay, and so that's again a straightforward geometric idea, but something something that you can prove algebraically. So I'd encourage you to work on that and to figure out how to write that out in some detail. So that is that. I also want to talk a little bit geometrically about adding two complex numbers. So we're thinking of complex numbers. We have a lot of different ways to think about them. We can think about a complex number z, and in fact, the book has a nice diagram of actually 5 ways to think about them so far. Okay, that's partway through chapter 1. So you can think about z as x plus iy, where I is this magic quantity such that when you square it, you get -1. That's one way to think about a complex number. You can think about a complex number as a pair of real numbers, and this is what led us to think about graphing the complex numbers as a plane. Okay, and so you can think about the complex numbers as a plane there. With an x coordinate and a y coordinate, and then you had this kind of non-intuitive multiplication rule, but otherwise that's a useful perspective there. And one thing that comes up in Calc 3 is there's an identification between a complex number, or I'm sorry, in Calc 3 there's an identification between a point and a vector. And of course you can talk about the point P, and P is going to be some point xy. And then you can also talk about the vector v, where the vector is the vector xy. And what that means, and these are similar ideas, and there's a corresponding one-to-one relationship between the two quantities. But in complex numbers, a similar thing happens. And we can talk about a complex number, x plus iy, or we can think about this complex number in terms of a vector in the complex plane starting at the origin. And so that, I think, identification is a very useful one, especially when we're talking about the moduli here. So if you were to have some number z, then the modulus of z would be the length of that vector. Okay, let's get rid of the, so the modulus of z is just the length of that vector starting at the origin and ending at z. And I think that that's a good way to think about the modulus in general. Okay, and so that same kind of relationship is there. They're not exactly the same object. Points and vectors are not the same, but there's a natural canonical one-to-one relationship that you can put them in. Okay, so so they're not exactly the same, but they can be treated almost the same in certain ways. The reason why I bring this up is that I want to think about adding complex numbers as adding vectors. And so if I were to think about z and z bar or z prime, and what that means geometrically to add them, I would think about here's z, and let's say here's z prime. Well, what I could do is we could imagine that these are vectors, and then we're adding them tip to tail. So what I mean by that is that you were to take this entire quantity and you would move it so that it starts at the same place as z. Okay, and so the new vector that you would get from the origin to the tip of z prime would be the sum of the two vectors. So let me write that. In fact, let's write, so we can think of this as z prime, and then this vector, which I'll draw in red, is going to be z plus z prime. Okay, and so you could think of this kind of the same way as you would adding two vectors, again, because there's that natural one-to-one relationship. And it turns out what's useful about thinking about the sum of two vectors is you end up with a certain inequality called the triangle inequality. About that is that if you were to think about this as the sum of the sides of a triangle, if you were to add up any two sides of a triangle, that sum has to be greater than the other side. That has to be true for all triangles. And so if you were to think about a triangle where the sum of the two sides was less than the third side, it would look like that. It's not. So what's useful about that is that if you were to think about this as the sum of the sides of a triangle, if you were to add up any two sides of a triangle, that sum has to be greater than the other side. That has to be true for all triangles. And so if you were to think about a triangle where the sum of the two sides was less than the third side, it would look like that. It's not a triangle. And so that's not a formal proof in any way. There are formal proofs out there. In fact, there's one in the book that I'd like you to read. But that's the idea. That's the triangle inequality. And this is a very ubiquitous inequality that it's just going to pop up over and over and over. So this is true for all complex numbers z and z prime. So this is, again, is called the triangle inequality. And it'll be very useful for us. This is a very primitive's not the wrong word, but it's a very early tool that we can use, very common. So that's the triangle inequality. There's other versions of the triangle inequality. There's the reverse triangle inequality. So let me just keep these kind of in a nice order here. So let me rewrite that. So there's the reverse triangle inequality that says if you want to look at z minus z bar, that's going to be greater than or equal to the modulus of z minus the modulus of z bar, except you have to take absolute values, because you could notice that without these absolute values here, the right side wouldn't be symmetric in z and z prime, but the left side would be. So you need the moduli there. There's another version of this, so z1, w1 plus, if you were to have all of these being complex numbers, and this is going to be less than or equal to the moduli of z1 squared all the way up to the moduli of zn squared, and then the same for w, moduli of w1 squared, moduli of wn squared. And in particular, and one way that we're going to use the triangle inequality over and over is the following. If you were to look at the sum of zi as I goes from 1 to n, so this is not a straightforward this is not a straightforward consequence of what we had, but if you were to look at this sum, what you would end up with would be less than or equal to the sum of the moduli. So the moduli of the sum is less than or equal to the sum of the moduli as I goes from 1 to n. And that's really, I think, a best way to think about that is that that's really an extension of this first quantity that we talked about. If you have z1 plus z2 plus z3, in other words, so just as an example, if you were to have z1 plus z2 plus z3, that's less than the moduli of z1 plus the moduli of z2 plus the moduli of z3. Really, all you're doing, if you wanted to prove this formally, is you're just applying this inequality twice. And if you want to prove that this is true for all n, so this is true for all n greater than or equal to 1, then you would formally do this by induction. Okay, and so that would be the method of proof there. I will let you prove this to your heart's content as much as you want to, but that is, I think, everything I wanted to say about moduli.